Hello, young chemists. What is up? Mr. Rosen here. Today we're going to be talking about Lechatellier's principle, which is related to equilibrium, named after a French chemist, Henri Lechatelier. So what does the principle say? What's it all about? What's the main idea? If you have a system at equilibrium, and the system at equilibrium is disrupted in some way, we say that the system has been stressed. Okay? So if something happens that disturbs an equilibrium, we have stressed the system. Okay? Lechatellier's principle states that when a system at equilibrium is subjected to a stress, the equilibrium will shift in a direction that relieves the stress or counters the stress or reduces the stress. So that's the big idea. Okay. Now, main ways that you can stress a system at equilibrium, one of them is changing the concentration of either a reactant or a product. So a change in concentration. And if you change the concentration of a reactant or a product, so you add a reactant or you remove some of a product, the system is going to respond by either using up what you added or making more of what was removed. So it depends on what is being added or removed. That could cause the equilibrium to shift to the left or the right, depending. The whole idea is that the equilibrium will shift to undo that stress. You can also change the temperature of the system. If you change the temperature of the system, the equilibrium will shift in a way that reduces the stress, and that depends on if the forward reaction is endothermic or exothermic. Okay, so if the temperature increases, the system will shift away from the energy value in the equation. So you might have some number of kilojoules or kilocalories or something like that. Or it might just say heat, or maybe it says energy. If the temperature decreases, the system will shift towards the energy value. Okay? And then we also have a change in pressure. Okay? If you have gases, this is very important. The system is at equilibrium, and it's in a closed system. So you could almost imagine it as you just have like a set, a fixed box, a fixed volume box. And inside of that box, you have some moles of gas. If you have more moles of gas in the box, you're going to have a higher pressure. If you have less moles of gas, you have a lower pressure. So if there's a difference in terms of how many moles of gas you have on one side of the equation, then you're going to have a response from the equilibrium when the pressure on the system changes. So if the pressure increases, the system will shift towards the side of the equation with less moles of gas. If the pressure decreases, the system will shift towards the side of the equation with more moles of gas. Because if you have more moles of gas in a container, it's going to have a higher pressure. So decreasing the pressure on the system, it will respond by going towards the side that will have a higher pressure. I think it's probably easiest if we just do some examples here. So consider the equation below. Right? So here's our equation, and it's all gas, and this is our energy value, our heat values on the left. So that means that the forward reaction is endothermic. The reverse reaction would be exothermic. So first we're going to do some change in concentration. So this is the stress, how the equilibrium is going to shift, and then how these other things will change. So if we add CH4, the system's at equilibrium. If we add CH4, the equilibrium can respond by going to the right, or it can respond by going to the left. Now, if the reaction goes to the right, what that means is these things, the reactants, are going to get used up, they're going to be consumed, they'll decrease, and these things, the products, will increase. They'll be made. The opposite is if the equilibrium shifts to the left. If equilibrium shifts to the left, then that means that these things are getting used up. They're getting consumed. In order to make these things, they're going to increase. So the whole idea of Lechatellier's principle is to reduce the stress. So adding CH4, if we add CH4, think, if the reaction went to the left, that would make even more CH4, right? That wouldn't reduce the stress, that would make it worse. So if the system's at equilibrium and we add CH4, the system will respond by going to the right. If it goes to the right, that will use these things up, right? In a sense, it will use up what we're adding in order to make more of these and get back to equilibrium. So in this case, equilibrium will shift to the right. And that means that our reactants are going to decrease and our products are going to increase. Next, we have removing something. Okay, so the system's at equilibrium, and we're going to remove H2. So we have an equilibrium, and we remove H2. How is the equilibrium going to respond? Well, if equilibrium goes to the right, more of these will be made, and this stuff will get used up. If it goes to the left, these things will get used up, and more of these will be made. So the stress is that we are removing H2. If we remove H2, the correct response to the stress would be to go in the direction that fills in what was taken out. So if we're removing H2, the system is going to go to the right. That will make more H2. It will use these up and make more of these, right? That would undo the stress. It wouldn't make any sense if we removed H2 for the system to go to the left. If it went to the left, that would use up even more H2, and that doesn't undo the stress. That makes it worse. So again, in this case, equilibrium will shift to the right. And that means our reactants are going to decrease, and the products are going to increase. Next, we have temperature to consider. So when it comes to decreasing the temperature and thinking, oh, well, is this going to go to the left or going to go to the right? How's that going to go? It depends on where our energy value is. And here is our energy value, heat. Sometimes you'll get kilojoules or something like that. So it's on the left side, so that means that the forward reaction, meaning going from left to right, is endothermic. So if we go from left to right, this process is going to require heat or use up heat in order to make these products. If we went to the left, these things would react to give you these products and produce heat. So it's exothermic in the left direction, the reverse reaction. So number 3 says we're decreasing the temperature. So if we decrease the temperature, the reaction can either go, equilibrium can shift left, or it can shift, left or shift right. Sorry, I said those backwards, pointed the opposite directions. So if we decrease the temperature, the correct response would be to go the direction that produces more heat, right? And that is going to the left, right? If we go to the left, these things are going to react to make these products and produce heat. If we're decreasing the temperature, it's going to respond by going the direction which produces more heat, because that reduces or relieves the stress. So in this case, equilibrium is going to shift to the left. And if it's going to the left, that means that these things are getting used up and these things are getting made. So these are increasing and the products are decreasing. Finally, we have a change in pressure. Okay, now pressure, it's all about how many moles of gas you have on each side. If we look at how many moles of gas we have here on the left side, this is 1 mole of gas, this is 2 moles of gas. So we have 3 moles of gas on the left side. And on the right side, here's 1 mole of gas, and here's 4 moles of gas. We have 5 moles of gas. Now, this system is in a, let's just think about it as a closed box, okay? It has a set volume. If we had 3 moles of gas inside that box bouncing around, that would exert some pressure. If you had 5 moles of gas in the same box, that would have definitely a higher pressure, right? Because more moles of gas are inside bouncing around. So if we stress the system by increasing the pressure, it can respond by either going to the right, which gives you more moles of gas in the box, or going to the left, which gives you less moles of gas into the box. If the pressure on the system increases, the response that's correct would be to decrease the pressure of the system. And to do that, the equilibrium would shift to the side that has less moles of gas, which in this case is the left side. So the equilibrium will shift to the left. And if it shifts to the left, that means that these things are being consumed, they're going to decrease, and these things are being produced, so they're going to increase. So the reactants increase, and the products decrease. Let's do a couple more example problems using a new chemical equation. So in this equation, again, we have all gases, but a different number of moles, and we're going to stress the system in different ways. We do have our energy value on the left side again, and sometimes it's on the left, sometimes it's on the right. So the first stress is removing N2 from the system. Okay, and N2, you can see here, is on the left side. So the system can respond to that stress by either shifting to the left or shifting to the right. Okay, now if it shifts to the right, these things are going to be used up in order to make more of these. Or if it shifts to the left, these two are going to decrease and these are going to be made. So if we're removing N2, if the reaction went to the right, that would use up more N2. And that would not reduce the stress, that would actually make the stress worse. The correct response, according to Lechatellier's principle, is if we remove N2, the system at equilibrium would respond by shifting to the left, because that would use up these in order to produce more N2. In a sense, we're filling in what was taken out. That would undo the stress. So equilibrium here is shifting to the left, and our reactants on the left side are increasing, and our products on the right side are decreasing. Next, we're going to add NO. So we're adding something on the product side. Okay, we're adding something on the product side. If the reaction goes from left to right, these reactants get used up in order to make more product. Okay, but here, we're adding NO. So if the reaction went to the right, that would make even more NO. That doesn't reduce the stress. So if we added NO to the system would respond by going to the left, because that would use up what was added. It would use up the NO in order to make more water and nitrogen. So again, our equilibrium shifts to the left, which means that our reactants on the left side are going to increase, and our products are going to decrease. Next, we have a temperature, increasing temperature. So if the temperature is increased, the system is going to go in the direction that is away from the energy value. Okay, so if the temperature is increased, if the system responded by going to the left, when the reaction goes to the left, right, the reverse reaction, heat is a product. Okay, so it's exothermic in the reverse direction. That's not going to reduce our stress. That's going to make it worse, right? If we increase the temperature, it's not going to go the direction that produces even more heat. Right? It's going to go the opposite direction because that requires that energy in order to form the reactants. In a sense, it is going to use some of it up. So here, our equilibrium will shift to the right, meaning our reactants on the left are going to decrease, and our products on the right are going to increase. The final stress is a pressure change, and when it comes to the pressure exerted on the system at equilibrium, we need to look at how many moles of gas we have on each side of the equation. Here is 2 moles of gas, and here is 1 mole of gas, so we actually have 3 moles of gas on the left side, and we have 4 moles of gas on the right side. Okay, now this whole system, right, it's a closed system, so you could think about it as in, let's just say, a fixed volume box. If you had 3 moles of gas in that box, it would exert some pressure inside the container. If you had 4 moles of gas inside that same box, there would be a higher pressure exerted because there's more moles of gas bouncing around inside the container. Okay, so if we stress the pressure by, we stress the system by decreasing the pressure, the system's going to respond by going to the side that has more moles of gas. Because if it has more moles of gas, that side would have a higher pressure. And that would be reducing or countering the stress, undoing the stress, getting back to equilibrium. So because we have more moles on the right side, our equilibrium is going to shift to the right, and our reactants on the left are going to decrease, and our products on the right are going to increase. In terms of our K value for all of these, right, K is going to remain constant for all of these except for temperature changes. Okay? The K is going to be different at a different set of temperatures. We discussed that in class in terms of predicting the size of the K. You can look at how your reactants or products are changing and get an idea of how the size of K will change. Well, this has been a video on Lechatellier's principle, all about equilibrium and stressing a system at equilibrium. Hopefully you found it helpful. Study, 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 work, work, work. See you back in class.